So this is going to be a presentation about convolution and a couple different methods by which to do it. Of course, they're all mathematically equivalent, but you can write the code from a few different approaches, and those will, maybe one looks cleaner, maybe one's more efficient. I mean, one is going to look the cleanest, one's going to be the most efficient, and the last is going to be the most obviously derived from the mathematical expression. So I'll get to that when I get to that. But just to start, I have created an impulse response before. I've shown how to do that. So just extremely quickly, I'm generating coefficients with a canned function to create a Butterworth filter, instantiating frequency vector, computing the transfer function, which is a frequency domain thing, and then inverse FFTing that to get the time domain thing, which is the impulse response. There are, because of the way I've done this, 48,000 samples of the impulse response, but I just really don't need all of them. So I'm just going up to the 100th index, and so to see that, you can see by the time I get to the 100th index, the impulse response has sufficiently decayed to 0. Now, this is an Iir filter, which again stands for infinite impulse response, and so it does technically have an infinite impulse response. There are feedback terms. However, it becomes increasingly trivial as we move on. So there's no point in including all 48,000 samples. It would just be impossible to look at, impossible to understand what was going on, and it would be a lot of multiplying things by tiny, tiny numbers that might as well be 0. So I'm also contriving an input. If we were really doing this with audio, we'd probably have something that was more like white noise or brown noise or some type of noise, but I'm going to use this X vector that just starts at 10 and then monotonically decreases. And again, I want to use something small so I can look at these graphs and understand intuitively what's going on, and using this thing that just decreases from 10 to 1 is pretty easy to understand. So we'll see these two interact in a second, but essentially my convolution is the input X passing through the filter H. So this impulse response represents the system. It's a linear system, and we can convolve these two things in order to generate an output Y, which is, we have our time domain input, and we can get our time domain output of the system, the filter, whatever. So here are my three methods in code. I'm going to start with the middle method, which I've called the summation way, and that's because the way I want to write this concisely mathematically translates to this method in code. So this is probably the least concise method in code. It certainly takes the most number of lines, but it's easiest to see the link between this mathematical expression and writing it in code this way. And this is probably the mathematical expression I want to use, or at least it's nice looking. It's simple. So for each index of the output, and we're calling the indexes n, and the output itself is y. I'm doing a few individual multiplications. So I'm doing n number multiplications. So be careful here. This asterisk in this case does represent multiplication. We also use asterisks to represent convolution itself. So I would kind of write convolution as h asterisk x, but then that convolution is the sum of these individual multiplications. So in this expression here, this asterisk is a multiplication. So we'll show a test case here for n equals 4, which will make a couple of these other ways to write it more obvious. But for our test case here, we can see, so since the indexing of h starts at the highest value, it starts at n, and it's decreasing because we're subtracting the value that's incrementing, we can see our h terms, or the indices of h in each of these expressions, are decreasing, whereas the input to the x function is the thing that is incrementing, and so the indices of x are incrementing. There would technically be 5 elements based on how I've written this, but the last element would be, so it starts at 0 and goes to 4, that is 5 elements total, but since I'm indexed at 1, h of 4 minus 4 is h of 0. There's no 0 with index, so it's nothing. So there are no non-zero terms out here. So I do have the plus dot dot dot. That also just helped keep these all lined up so you can look at them vertically. You can see this decreasing and increasing behavior. So this is really simple to write in code. I just want to go up to the nth element of each of these two vectors. I want to flip the h vector and then multiply them element-wise. And so that's all I'm doing. I'm going up to the, in code I wrote it as k. I know, maybe confusing. So I'm going up to the kth element, flipping h front to back, and then multiplying them element-wise. It's my dot multiply, and then summing them. So this is the most simple in code. It's really pretty. It's still not the fastest. Using this, the h is 100 elements and my x is 10 elements, so that's really tiny. So the difference here was maybe like 1 millisecond to 2 milliseconds. But if you're expanding this out to use it for something more practical, that's a 2-to-1 ratio. That's pretty significant in terms of time. So there's another way to think about this. Of course, we'll show the mathematical equivalency, and this third method is actually going to be the fastest. At least I'm using MATLAB here. Well, I'm using Octave, not MATLAB. But this was what I found to be the most computationally efficient. So I'm gonna write this out horizontally now. So here are my individual terms. It's the same thing. H is decreasing, indexes of x are increasing, and there's just spaces in here, not plus signs, but you know that I'm just taking these individual terms and adding them together. So I'll stack the previous values of y above here, and you'll see a different pattern arise, which is now if I look down vertically, I can see that I just have h, the entirety of h, essentially multiplied by a single value. It's always being multiplied by x of 1. So really everything here is just h multiplied by the first element of x. This is the entirety of h multiplied by the second element of x. This is the entirety of h multiplied by the third element of x, etc. Obviously, if you extend, y of 5, y of 6, these columns all get longer and longer. And this is often how convolution is shown graphically. This method is really easy to look at graphically. It's not super intuitive to show mathematically or to explain, but if you look at the first element of the output, it's just h of 1 times x of 1. The second element of the output is still that second element of h times the first element of x, because it was the entirety of h scaled, but now I take h and I just move it over 1, and now it's being multiplied by x of 2. So because these elements are mismatched, the element of h that I'm multiplying by a different element of x means one of them has to be moved over. So x stays stationary and h gets moved over 1. So here, x is still stationary. I'm at the third element. I'm at the third index, but now I've moved h over twice so that I can multiply the first element of h by the third element of x. So that looks like this, and again, this will look more, or make more sense when I show it graphically, but in order to move, kind of slide h along like that, I have to put some zeros in front and have some zeros appended, and I'm doing that dynamically. For y of 1, all the extra zeros go at the back. For y of 2, there's 1 0 at the front and 9 zeros at the back, so on and so forth. So I have to pre-allocate this big array or all these different, I'm just taking the entirety of H and scaling it by X. I have the entirety of H just at these different magnitudes essentially stored in this array. So, because there are 10 elements of the input, that means that the array stores this H times X 10 times. And the length is really H, or the length of H plus the length of X, because, again, I have to append these zeros in order to account for the sliding. So you should recognize that this shape, in general, all these things are the same shape. These are all my different H's that are scaled by all my different values of X. So there should be 10 of them, and it's easy to look at and understand because my X was just that thing that was monotonically decreasing. So it started at 10, then went to 9, then went to 8. So the blue one at the top is my H times 10. The red one is H that's slid to the right one element and then multiplied by 9. The yellow one is my H that's slid to the right by 2 elements and multiplied by 8, so on and so forth. And then to find my output at any of these given indices, so for example, at the 20th index, my output, y of 20, here is the sum of all these individual vectors at their individual 20th indexes. So it's easy to see this graphically and think about how to do that mathematically. It's not necessarily simple to think about this mathematically and how it relates back to our original expression for convolution, but hopefully you've kind of seen the individual steps, so you can see this graphically, which is easy enough. It's just kind of an easy operation to think about, and then you can relate that back to this, which relates back to this, which relates back to this very concise mathematical expression. So, you'd often see it mathematically this way, but geographically this way, and those two things are maybe kind of disparate, but that's how they tie together. So this way ended up being the fastest for me in Octave. I don't get ever much into the weeds of really implementing things in real time and worrying about computation speed, but you can certainly be filtering some hefty vectors, an entire song sampled at 48 kilohertz, for example. You're talking about a few hundred seconds, where each second is almost 50,000 samples. So that's a lot of computation. And the size of the array that I would need to pre-allocate for this method would really bloom in that case, and maybe it wouldn't be faster, so maybe it's only faster for these smaller vectors. I haven't investigated that. But in any case, a few different methods here, and the different methods might be better given on the application.